In this lecture, let's understand the MOSFET operation. Remember, we are just understanding it qualitatively. We are not understanding it quantitatively. We are just understanding it with qualitative uh, discussion. So, it is very clear that if the VGS will be less than VT, that means there is no channel between source and drain. Between source and drain, you have a depletion. 100% there is no current, there is no ID. This is very clear to you. Now if VGS is greater than VT, there would be one ID. Definitely there would be one ID. And if VDS is less than VGS minus VT, because why this conditions comes, because if the VDS will be less than VGS minus VT, till this point there will be a channel between source and drain, right? Till now, what we know is, we know that if the VGS would be greater than VT, there would be a channel. But to have a channel, VGS has to be greater than VT plus VDS should be less than VGS minus VT. Then only the channel will exist. And if the channel will exist, we call that current as a linear current. Okay, so please remember this thing. The channel will only exist when two conditions will meet. One, VGS has to be greater or equal to VT. Number two, VDS has to be less than VGS minus VT. If these two conditions are met, there would be a channel between source and drain, and the current at that time, whatever the current flowing at the time, will be known as a ID linear. Now, qualitatively, we discuss why this ID will be this. So, we can see from the measurement graph of the ID versus VDS of a MOSFET, what we can see is, for a VGS, let's say for VGS equal to 1 volt, VGS equal to 2 volt, VGS equal to 3 volt, the ID is basically depending upon the VGS minus VT. Okay, let's say the VT is 1 volt. Okay, so the ID is basically depending upon how much excess voltage beyond VT you are applying at the gate. So definitely ID will be proportional to VGS minus VT. Now with a small voltage of VDS, ID will be proportional to VDS. ID will be also proportional to VDS. You can see that for a small voltage, you can see here, for a small voltage, IDS is linearly increasing with the drain voltage. So as soon as the drain voltage is increasing, ID is also increasing. VDS is increasing, IDS is also increasing. VDS is increasing, IDS is also increasing. Okay, so ID will be proportional to VDS also. But if you further increase the voltage with the same increment in the VDS, you don't see the same increment in the ID. ID is less. Why ID is less? Because now VDS is increasing, and this VDS, so earlier the VDS was very large than VGS minus VT. Now since VDS is increasing, so it is approaching towards VGS minus VT. So if it is approaching towards VGS minus VT, definitely the channel width is going to decrease. So if the channel width is going to decrease, definitely the channel resistance is going to increase. So that means with the same increment of the VDS, so you don't see the same increment in the current. However, the current is lesser. That means current follows somewhere over here. Current follows the square law of square law. So current is proportional to the square of VD. So there is a term which is square of VDS in ID. So this is how we can qualitatively understand, and we definitely know that the current would be proportional to mu n, the current would be proportional to C, the current would be proportional to W, and the current would be anti-proportional to L, because if L will increase, the resistance of the channel will increase. Okay, so this is how you can understand qualitatively. Now come to the saturation point. Saturation point meaning when VDS is becomes equal to VGS minus VT or greater than VGS minus VT. What we know is, definitely at this point the channel at the drain end does not exist. Channel at drain end does not exist. does not exist. If you want to understand this in a more detail, I'll make a separate video, but here I just wanted to I wanted to have a brief discussion over the IV curve. So when this, so the channel at drain and does not exist, and the current becomes saturate. You can see the current becomes saturate. If the current becomes saturate, that means the current is independent to the drain voltage. So we need to remove the VDS from this equation. How to remove? Because this happens at VGS equal to VDS equal to VGS minus VT. So put the value of VGS minus VT, VDS equal to VGS minus VT in this equation. As soon as you put this, you will get, so remove this, you will get this equation. So this equation is for the ID set. But what happens is when you actually, so this equation is completely independent to VDS. What does it mean? The current, the current has to be completely constant with respect to VDS. But when you actually draw the curves, actually take the measurements, you see that no, the ID is, it is still little bit depending upon the VDS. It's very it's with a very small amount, it's depending upon the VDS. So what we need to do is we need to finally write ID set, which will be equal to this Kn by 2. So Kn is basically mu n Cux W by L, Kn by 2 VGS minus VT whole square, and you need to multiply this with the very small factor lambda VDS, because it is a very small factor lambda, and it is proportional to VDS also. It's not constant with respect to VDS, it's depending upon VDS. As soon as you are increasing the VDS, the current is going to increase with the VDS. So but that dependency is very small, so we have multiplied this with a very small factor lambda and 1 plus this. So this current is already there, plus you have some small amount of current. That small amount of current is the original current multiplied by this very small factor. So the overall current would be then the saturation current would be then 1 so this mu n Cux divided by 2 W by L VGS minus VT whole square 1 plus lambda VDS. So whenever we will be using the current, so we have three different equations, the three different current equations. So ID will be 0 whenever you have VGS is less than VT, and whenever you have a VGS greater than VT and VDS is less than VGS minus VT, we call it a linear region of a operation. And at that time, this is the current equation. And whenever you have VGS is greater than VT and VDS is also greater than VGS minus VT, then there would be a saturation current. So depending, so first you need to find out the mode of the transistor, and then you need to use the particular equation, the corresponding equation. Thank you.